right. Now, if you guys figured out the graph, which one that matches the 2 cosine x plus pi over 4? Last one, right? Last one. So you see that the vertical stretch, right, by 2 units, and also it shifts to the left, right? There you go, right? Just make sure that you know this is, I mean, not the hardest kind of a test problem, but also that's like a medium to advanced, right? A little bit above medium level, right? Now today we're gonna have to do the remaining 4 functions, right? So, and hope that you have the reference sheets that I gave you the other day, right? And I'll teach you how to use it. But let me help you to seriously look into the detail of the tangent graph. Okay. So let's study its behavior. First off, you know that this graph is not the full version, right, of the tangent. Right, you have this graph, copy and paste it, right, that extends to positive, negative, infinity. But you notice right away, there are 2 VA, right, or vertical asymptotes. One at negative pi over 2, the other at pi over 2. Is there a way to understand why the function has a VA? VA, vertical asymptote. Which means that if you're taking the input for the tangent as close to the pi over 2, the function will grow as high as it can. And it doesn't even have a boundary. Okay. Oh, the good news is you guys can use scientific calculator from now on. In our assessments, right, quiz tests, right, even in class, you want to pull out your decimals, scientific calculator, but not graphing. You still are not allowed to use graphing calculator in our assessments, but scientific. Now, there's an easy way to understand why there are VAs. You guys remember that tangent is sine divided by cosine, right? So let's see, what is tangent? Pi over 2, which is sine pi over 2 divided by cosine pi over 2, right? So if you have a scientific calculator, if you have the decimals pulled out in front of you, go ahead and evaluate what is sine of pi over 2 radians, what is cosine pi over 2 radians. If you don't like radians, do the degree. Sine of 90 and a cosine of 90. How much is sine 90? Yes, it's 1. What about cosine 90 degree? 0. There you go, right? So now if you want to try tangent 90 or tangent pi over 2, it says math error, right? Or whatever error, right? But what is 1 over 0? Undefined, right? That's why the calculator complains, right? But I mean, you're going to go to calculus, and I hope that you're not going to tell the calculus teacher that, oh, 1 over 0 is undefined, right? Well, in some sense, you maybe back in elementary school, but let's understand what is 1 over 0. Okay. So 1 over 0, yes, it's undefined. But the problem is, I mean, what does the 0 really mean, like in a number system? It's such a weird number, right? 0, it means nothing, right? It means that the smallest number possible. You might say, well, no, I mean, I know the smallest possible number will be negative. Say negative 1,000, negative 1,000,000, right? But I'm not talking about the direction. Like a negative means it's go in a negative direction, right? So now you guys know what is the freezing temperature for 32 degree, right? So now that's Fahrenheit. So in Celsius, it's 0 degree, right? In well, if you go into physics, they'll tell you that in thermodynamics, it's not 0 or 32. It will be something else, right? And in the universe, there's no negative temperature. It doesn't make any sense, right? What do you mean by negative temperature? Huh? Okay, good to know. All right, now let's say to me, 0 is the smallest number possible. Think about this. If I say, hey, the least amount of homework I can give you will be 0 problems, right? That's the least I can do, right? But what if I say, I want to give you even less problems? I'll give you -10 homework problems. What does it mean? -10. It's like you making problems for me to do. But there's still homework problems, right? I want to promise that there's no homework because I don't even want to give a problem. I want to grade the problems, right? I want 0 problems. So 0 is the smallest number you can ever think, right? So now let's see. Let me play with the 0 on the denominator. So I want to make it so small, but not really exactly 0, right? Is that a small number, like a super small? You know what? As long as decimals let me do it, I can make it as small as I want, right? I can keep pressing 0 for an hour. But what is this number? Is that big or small? Big, right? It's insanely big. Well, I mean, it does make sense. I don't have to tell you that because the smaller the numerator, the bigger the fraction, right? And that's why, now, coming back to, let me put it this way. What if I said I make the denominator infinitely small? Because, the smaller the denominator, the bigger the fraction. If I make the denominator infinitely small, the fraction will become infinitely large, right? Infinitely big. And we have a term for it. It's called infinity. So don't tell me undefined anymore. You have a way to define it. It's called infinity. Now, to go back and see, does it make sense now when the sine is 1, but cosine is 0 at pi over 2, you have 1 divided by 0, which is something super, super small. However small you want it to be. And guess what? Tangent is going to be as big as you want it to be. How big that is? Infinitely large. And we have a term for it, positive infinity. You might say, what happened to the other side? Well, guess what? The sine will be -1 when you evaluate the sine at negative pi over 2, but cosine at negative pi over 2 still be 0. A -1 divided by 0, it's making it infinitely large. 1 over 0 is still infinite large, right? But with a negative, it's making it infinity going the wrong way, right? So it will be the opposite direction, right? And that's why, so you have 2 VAs at this point, at the negative pi over 2 and pi over 2. And also you notice that the 2 VAs defines the period of tangent. It's the width of that repetitive part of the graph, which later get copied and pasted, right? The trend is also kind of nice because it keeps, extending, right? Keep increasing, right? Now, my first period student had a good question. She said, wait, how come that, what is the period of the tangent function? What is the amplitude of the period? What is the amplitude of the tangent function? Amplitude. We have amplitude for sine and cosine, right? But the tangent is going to go all the way up, right, to positive infinity, or going all the way down to negative infinity. Does it still have amplitude? If you insist that it has infinite amplitude, right? But that doesn't make much sense. So I'll say that amplitude is not even defined for tangent. It does not have amplitude. Okay. Now, this is the whole package of the tangent graph. Okay. Even though that we can calm ourselves down and say, let's focus on the centerpiece because that's the piece I just showed you, right? Oh, by the way, so tangent is an R function. That means if you hold the graph, let it spin about the origin, do a 180, rotation, the graph's going to look the same. Okay. But you do have to deal with, infinite many pieces. Right? But does it make sense that they say the domain is all real number except for the odd multiple of pi over 2, which means that you can take the x or the input to be any numbers you want, but you have to avoid pi over 2, 3 pi over 2, 5 pi over 2, or the negative versions. I mean, you can remember, exactly what they say. I'll hope that if you are able to recall in a test that the tangent graph looks like that, it has two VAs, one at negative pi over 2, the other is pi over 2, and you can predict where those remaining VAs going to be using the period. Since you know that the graph's going to repeat itself after pi units. So if you start from pi over 2, go to the right by another pi, you're looking at pi over 2 plus pi, which is 3 pi over 2, you're going to see another VA. And another VA, right? Or you go the other way. But you know that every time there's a VA, you're not supposed to reach exactly where the VA is located for the input. You just cannot take the input to be exactly pi over 2, because if you do that, it blows up, right? And therefore, if you know how the graph, looks like, you would have predict there will be a certain amount of points you have to skip, right? Now, when it comes to the range, that's obvious, since it could go all the way to positive infinity and negative infinity. So it does cover all real number vertically, right? So whatever number you want to get, you can get it from the tangent. You can get as big or as negative as you want. You just have to play with the angle. And you only have to do the angle in between negative pi over 2 and pi over 2, because you want to have a big, number, and you can do an angle that's super close to 90, right? And let me show you in a calculator, because now, you guys are allowed to use it and use it to, assist your understanding, right? So let's say I want to get an insanely big value from tangent. So I'll do my bad. So 89.9 degrees. So that's super close to 90, right? So now it's getting me only 572 something. So how am I going to be able to get even bigger? Well, I cannot go beyond 90, or cannot take exactly 90. Oops, too big. $89.999. And see how big that is? 10 to the 10th power, right? So that's why the closer the angle is to the 90 degree, the bigger the tangent value is going to be, right? And that's why, it does make sense, because it does blow up, right? At pi over 2, or even negative pi over 2, right? And all the other locations. Now, what about the cotangent graph? Take a look. That's the cotangent graph. Or if I, showed you this graph, all of a sudden you probably didn't realize it might not be a tangent graph, because they look so similar, right? The shape is the same, the period is the same, right? And also, it does have VAs. It does extend, right, to positive infinity, negative infinity. That means all real number for the range, right? But there are actually two major differences. Can you guys name those two? The two major differences. Okay, Juwan, what is that? Okay, so the graph of the cotangent seems to be flipped right? Compared to the tangent. So that's one major difference, right? What's the other one? Next. Okay, so like where the graph intersects, right? Good. All right, so now let me put the tangent graph on the same grid. And you can see what Max and Juwan mentioned, the two differences. So Juwan says that the graph of the cotangent seems to be flipped based on the tangent graph. And Max says that, well, it didn't start from the same zero location, right? So I draw two VAs, one at negative pi over 2 and the other at pi over 2, right? And all right, so the tangent graph is a ascending graph, like a increasing graph. All right, so that's the tangent. All right, so now first off, as you can see that it intersects 0. But now the cotangent intersects at pi over 2. Also, it seems that the trend, instead of going up, the graph is descending, right, for cotangent. That means it must have been flipped, right, left and right. And these are the two major differences. And it turns out there is a much easier way to even, alert yourself to those two major differences. So let me remind you an identity that you have learned before. I claim that cotangent x is tangent pi over 2 minus x. Can anyone identify that identity? I want to know the name of it. Yeah, Amaya? Co-function identity. Because the function cotangent, right? It's the co-function of tangent. But it might not be that obvious because I didn't put tangent 30 equals cotangent 60, right? Otherwise, you would notice that those angles add up to be 90. But think about what did I do? I was subtracting the angle from pi over 2. Pi over 2 is just 90, right? Subtracting something from 90, you get its, complementary angle, right? But if I write the tangent pi over 2 minus x in a better way, could you remind me, if I were to start from the graph of a tangent, what do I have to do to the graph to get cotangent? If there's a negative sign in front of x and there's a face there. So what does that negative sign in front of x does? It flips horizontally, right? And that's why the graph of tangent get flipped. After that, what is the phase shift? Well, it's pi over 2, right? But in what direction? Why is it left? Inside, opposite, so that's why there's a plus, it's left. But what has happened before the shift? So that has messed up the orientation. That means the safe way for you to get the direction is to factor out that negative sign, like you would have done if there was a 2 there, right? Negative of x minus pi over 2, right? So it is a horizontal flip. Once that's happened, you are shifting the graph to the right by pi over 2. Let's see if it makes sense. Here, the tangent intersects the 0, right? Flip it, still intersect the 0, but shift it to the right. All right. Now, be careful with the orientation. So I think that I said it, in the past. So if you use the FaceTime camera, right, and you're holding a sign, say "I love you," when you look at it, it says backwards. But that's not even you love I, So the letters that they reflect, right? It's just like you look into the mirror, you want to fix the earring, right? You're on your right ear, right? It seems that you're touching your left ear in the mirror because the orientation is flipped, right? So you have to be careful with the orientation, and you have to do like a double flip. But why would you do that? back out the negative sign because you have taken care of the flip. See what's really happening to the shift. Anyway, so the cotangent is nothing but a flipped and shifted tangent, right? Whatever you know about tangent, then you should be able to apply it to, the cotangent just with a flip and a shift. So that's why on the reference sheet, the bottom left shows you the standard graph of tangent. This is cotangent. If you want, you can keep looking at them, right? Using them for your homework. But later on, you'll realize that I never have to remember the cotangent. It's just too much work, right? I remember the tangent, not because I wanted to. I have no choice, but I keep using it, right? It's like you'll never forget about your own cell phone number, right? Because you just keep using it. John, you have a question? Yeah. No. All right. All right, now. I think that we probably did this already, right? So let's move on to this one. So I'm going to write it down so I don't have to, let me see, y equals negative tangent, right, x minus pi. So now, I'll give you 1 minute to match one of those graphs to that equation up there. Negative tangent pi, tangent of x minus pi. Yeah, this is an overall negative sign. All right, so you guys ready? All right, yeah, raise your hand. A, B, C, or D? Wow, so I mean, everyone agreed, right? It's letter D, right? Last one. There you go, right? So if you remember, or you don't have to remember right now, you're not gonna be taking a quiz anytime soon, right? I mean, the test is in about 2.5 weeks or something like that. Sounds very encouraging, right? Only, yeah. So now if you're looking at the bottom graph, the bottom left, right? So you know that, I mean, it has to be shifted to the right, right? By pi units. And then the negative sign overall is gonna flip it vertically. And that's why it looks like that, right? It's supposed to be going from the bottom left to the top right, but it's flipped. But now what's interesting is, how come that it still intersects the same place as before? Because the tangent, look, if I were to draw the tangent graph, it's going to be something like this, right? And there's one over here, right? So I have flipped it, and turns out that's the only thing I did. Didn't have to worry about the phase shift. I'm not supposed to shift it to the right by pi units. Well, it turns out I did. You just couldn't tell because I haven't shifted the same amount as the period. So that means it's even kind of silly to worry about the phase shift, because if the tangent has the period of a pi, it makes no difference to the tangent when we add or subtract the pi. It's just like to the sine and cosine, they don't care about you adding or subtracting 2 pi. It won't make any difference. Tangent, if you add or subtract 2 pi, it will still be the same as before, just like all the other functions. But tangent can do a little bit more. If you even add or subtract pi, it does become the same, right? So that means, technically speaking, this is nothing but negative tangent of x. That means, indeed, you only have to worry about the vertical flip. Okay? Now, let's try one more with the cotangent. All right? Wait. I get it. You know, it's like I don't like all the co-functions except for cosine. You know, but then I don't like cotangent, cosecant, and secant. All right, so I think that's the graph. Yeah. So now go ahead, match the graph with 2 times cotangent of x. Hey, feel free to look it up. You know what the cotangent look like on the reference sheet, right? I mean, if you don't get to use the you know, cheat sheet in the test, then appreciate it, you know, before the test. Two times cotangent x. So cotangent x looks like there's only one thing I have to take care of, right? That factor 2 all the way in the front. So what do you say? If you're ready, let me know which one you're going to pick. A, B, C, or D. All right. So yeah, it's letter C because it looks just like the original version, right? So now you think that, wait, why you have a 2 there? You know, is that supposed to like a stretch the graph? Yes, it does, but you just couldn't tell because it's extending to the vertical direction anyway. You stretch it, make it 2 times as tall, it looks similar. But at least you know that it's not supposed to flip it. It didn't do any flip, right? And there's no shift. That's all, right? Yeah. What's wrong with the B? Now, cotangent graph without any shift, it will be something like this, right? That's a cotangent. But if you do it 2 times, it's only going to stretch it, but it's not supposed to shift it. All right, no problem. All right, so now we are ready to deal with the hardest kind of graphs, right? That's the cosecant and secant. So like right off the bat, you see this just ugly, right? Well, I mean, it might not be really that bad. At least it's symmetric, right? So it's a very smooth, right, symmetric U shape, right? But sometimes it opens up, sometimes it opens down. But there's still a way to understand it. So that will help you to, you know, utilize or apply that to certain problems. So why don't I remind you how the cosecant and a sine are related. Do you see that they actually plot the graph of the sine, right, with the wavy dashed line? So again, let me remind you, cosecant is nothing but 1 over sine. Okay. And now let me point at the maximum, one of the maxima, right? One of the maxima of sine function. So at pi over 2, sine reaches the maximum at 1. But if you are getting the reciprocal of the sine or the cosecant, when the sine reaching its maximum, cosecant must reach its minimum, right? Again, the same reason, the bigger the denominator, the smaller the fraction. If the sine is reaching its maximum, then cosecant must be at the minimum, right? And therefore, you see this part of the graph? This is indeed the lowest point of cosecant. See that? Now, what about this point? That is the minimum of the sine, right? But if you're making a denominator small, you're making a fraction big. So that's why if sine is reaching its minimum, cosecant is going to be at its maximum. That's why it's the highest point of the U shape, right? All right. But what about the x-intercept? Look at this point. At 0 degree or radians, sine is going to be 0. 1 over 0 is what? Don't tell me how to find. Infinity. That's why you see that the graph go all the way up, right? And you know, you're probably gonna hear your calculator instructor say that that graph blows up at 0, right? Also, what about this guy? At pi, sine is also 0, right? So now you don't have to remember it because just type in a calculator. Pi is 180 degrees, sine 180 is 0, right? And it blows up again, right? But why is that something that goes all the way down? I thought that at pi, sine is 0, right? It's supposed to go positive infinity. But why on the other side of pi, it goes down? But it turns out that you see this part of the sine graph is most likely below the horizontal axis, so it's negative, right? So it's basically you're having a negative infinitely small, right? A negative infinitely small denominator. For example, like a point right there, super close to pi, but a little bit to the right of the pi. Sine is negative 0.00000001. So it's making the fraction infinitely large, but in a negative direction. It's going to go all the way down, right? But again, there's too much reasoning. You could do that every time, you know, in a test, but it will be taking a lot of time. So I think I've told you one day, right? So to graph the cosecant, it's as simple as just grab the sine and go to every peak and a trough and flip it. So you see that there's kind of a U shape, not quite a U shape, right? So at least it's something that opens down, right? Keep that maximum, flip it up, but you have to realize that it does blow up, so it's not going to touch these two vertical lines. And where are those vertical lines? They're always going to be at the x-intercepts of the sine function. Every time you see a 0 point or the x-intercept of the function, you're going to draw a vertical line. That's the vertical asymptotes for the cosecant. But the shape, it will just be a U shape, and you can kind of remind yourself why it's a U shape is you flip it up, right? For a peak, go to the trough, find this minimal, flip it down. That's all. And keep doing that for every single peak and trough. And also, you see that it's indeed still periodic. Some people worry about, I mean, yes, we get it. The sine function is periodic because it have a nice wavy line, right? Do you see that a U shape up, a U shape down? These two get together is a pattern that reappears here and there. And it goes all the way there, right? So this is a single piece that gets repeated. Not just one single U, it's one U up, U down. Okay? All right, now take a look. Oh, yeah, go ahead. Take a look at the last one, secant. Okay, so now it starts to make a lot of sense, right? If you grab the cosine, everyone knows how to grab the cosine, right? Find out where the x-intercepts are. Go ahead and draw a whole bunch of vertical asymptotes and go to the peak in a trough, flip it up, flip it down. That's all, right? So I said that, you know, you're dealing with the hardest to graph, but now once you understand it, maybe the graph of a secant and cosecant are one of those easiest to graph you have to deal with. But don't get me wrong. What I just told you is like a way to understand and remember those graphs and how they're related. They're not that accurate. When I say flip it up, you know, how do you know exactly how you're going to draw the curvature, right? But think about this. The reason why we teach you guys the graph is not because we want you to create a graph by hand. We want you to be able to read the graph, okay? Once you have a graph, you know everything about a function. There's nothing you don't know. So when you practice, you know, you just want to know the trend. You want to know those crucial points, like the minimum, maximum, right? Whether it blows up a certain way. Why would you care how much it curves? So let's say, I was asking you, how much is secant pi over 4? Pi over 4 is somewhere here, right? 0 degree, 90 degree, pi over 4 is 45 degree. So if you had a perfect graph from a computer, you would go up and get it. Would you actually trust your own graph? Hand graphed it and say, oh, I want to find out what is, the secant, cosecant, secant, right? Pi over 4. No, right? And also, not to mention, why would you do that? You have a scientific calculator. Plug it in, right? Secant pi over 4 is whatever it is, right? So therefore, we'll teach you the graphing skills so that later you're going to understand the graph even better. Anyway, so now let's test your, or let's say evaluate your understanding at this point. All right, so we have a, let me, guys, now, there might be some multiple choices are like this. They tell you, hey, graph 1/2 secant pi x, but they provide you a grid. In pre-cal, not in pre-cal, in college algebra, I told my students, ignore that. You don't have to graph it. I'm not going to even grade it. But this time, if you have a grid like that, do graph the reference, not that function, the reference. So you're going to, based off the reference, figure out which options. Now, what will be your reference graph for -1/2 secant pi x? Cosine, right? So let's do that. We have, so I want to see -1/2 cosine pi over x. Okay, so now it's a cosine, right? And it doesn't do any shift, right? There's no phase shift, but it does get, like a squash, right? Squeezed. So I'll say that it looks something like this. Wow, that's, you know what? It's -1/2. It will be something like, okay, how much is the period, you guys? Can you tell me? Pi x, the period is supposed to be 2, right? 2 pi over pi, 2. So 2 is somewhere, maybe, let's see, that's one. I'll say that's roughly somewhere here, right? So I'm going to do a graph. Okay, is that good enough? First off, it is a cosine. But you say, why didn't it start from up there? You have a -1/2. It does the vertical flip, right? Why it doesn't go between -1 and 1? You have a 1/2, right? It squashed it. And it doesn't go all the way to, 2 pi, because, you have a pi that make the period to be, 2 units, right? So that's a graph, and you can draw up more. I just make it something like that, right? So now what you do, go find those x-intercepts, right? There will be VAs. Oh, I'm kind of bad with straight lines. See that? I'm actually pretty good at drawing curves. The straight lines are hard. Right? So now you're gonna go to the peak, right? Flip it up. Go to the trough. Flip down and up, right? I mean, you get the idea. Right? So now let's go ahead and match. Oh, I wish I can show you all. Well, I wish you can see what's up there. And do you see that? Oh, wait, where's this one, right? Yeah. So that's all you have to do. Okay. Now, if you're still a bit concerned, like for some reason that there's nothing in B and C, right? And that's why maybe when we pick the problem, that those kind of questions should be skipped. But if you want to see that whether letter A or letter D, right? So which one is right? So let's find some point, and let's try to be nitpicky. Do you guys see that letter A has a y-intercept? Okay, so what we are plotting is negative 1/2 secant pi x, right? So let's say negative 1/2 secant pi x. How do you find the y-intercept of this graph? How do you find y-intercept of a graph in general? Right, but algebraically, you're going to substitute 0 for the x, right, and evaluate it. You have a eccentric calculator. Here, type it in real quick. What is negative 1/2 times secant 0? Watch the recording. How much is it? Negative 40? Negative 45? Wait, secant 0. Negative 1/2 times secant 0. You do the inverse? Yeah. Oh, you can take this one. Yeah, it's probably yours because you weren't here last time. Yeah. Okay, go ahead. As the reason why that you go with the inverse, right? So yeah, cosine inverse, that's the inverse function. Now the reciprocal, yeah. What you do is you do cosine. Exactly, you do cosine 0, then flip it, right? It's 1/1 still 1, right? Take the negative 1/2. So it'll be negative 1/2, right? Does it make sense that it intersects at negative 1/2? All right. So now think about this. If you use the scientific calculator, you would have picked the letter A anyway, right? But now you have a backup plan, right? If you don't bring your scientific calculator or you forget about how to use it, right? Then, yeah, Maya.